Okay, it's 8. Shall we start? Oh, okay. Andrew can hear me. You're alive. Good morning, good afternoon, everyone, wherever you are. Welcome to IETF 112. And we are opening routing working group session for IETF 112. So for a change to this IETF, we've got single 2-hour session. And we figured out that probably still not enough time. We had to decline some presentations, so we'll try to have 2 sessions next IETF. Moving. Ingrid, can you hear me?
Yes, there should
rising.
be
Okay.
numbers under your slides to flip through.
Yep. So not well, you've seen many times. We would like to repeat that by participating in IETF, you agree to IETF process and policies. It has been paid a lot of attention to sometimes behavior that doesn't belong in IETF. We would like to remind you that as participant, you agree that you will work respectfully with other people, you don't harass other people. And while we don't see it in routing working group, there were some cases where it did happen. Please keep it this way. Please be friendly to others, please respect other ones. And all the documents are below for your information. So IETF policy requires to review and disclose intellectual property as in RFC 8179. Routing working group specific rules, we will ask you to disclose APR on document adoption and working group last call. And unless all authors and contributors have responded, documents won't progress. Please remember that. So agenda for today is we'll have update on the SAR6 pass egress protection. APN folks will be talking about changes seen last time, and we would like them to focus on explaining what changed and why they think the document should progress. New work is related to satellite communication, as well as cloud through optical problems and cloud network integration and PPR. As part of larger focus, we're going to have HPC++ presentation, which is talking about high precision control needed in large data center networks and potentially applicable to routing as we go forward. And then since BFD doesn't meet, we've got presentation on signal degradation from BFD. We've got the RFC 9067 published, which is fundamental for BGP YANK model and actually all routing YANK models in IETF. It's a really serious milestone, and congratulations to the authors and IETF. We didn't adopt any documents. In terms of existing documents, we've got QS model, and it's being reviewed by Document Shepherd, and we finally reviewed. And thank you, co-authors and engine working with co-authors of removing norm has retired. RIB extent is pretty much ready for working group last call, and BGP peak is pending AD review. To answer Stuart's question, it's up to you. We can do the slides, or you can do up to you. Really let us know. So TILFA, Stuart Brandt is shepherding it, and authors still need to address all the comments. ATN BGP has been requested to go through working group last call. We'll start reviews next week. and the service protection will be presented today. And we are going to start using Wiki like everybody else in IETF to start progress, to publish some additional information, metadata. Soon we will update you on the URL and what to do. So thanks, and I think unless there are any questions, we are ready for the presentation. Lana, would you want us to present slides or do you want to share yourself? Are you there? It's surprisingly quiet. I don't hear anything.
Huanmo, are you there? I don't see him online. Okay.
Yes, sorry, I just clicked the unmute button.
Okay, so would you want us to share slides or are you going to share yourself?
Can you upload the slides? The simple slides.
I uploaded. If you want to present yourself, you can use the share preloaded slides icon next to the raise hand icon. Join queue.
Share slides, ask for share screen?
Yeah. You can find your own slides and flip it through.
It's second icon from the left. It says share preloaded slides.
Yes, I ask for share slides. So can you see my slides?
Only Cheers have that icon.
No, everybody has. You should be able to present.
Okay, I'll do it. We are really tight on time.
Reason otherwise, I think.
It's just all slots have been taken. That's weird.
Okay. Yeah, maybe easier for you to just upload the slides.
Okay.
Yeah, I can see them. It's coming up. Okay.
Yeah, I can see the slides. Good. So hello, everyone. Today, I'm going to talk about SRv6 path egress protection. Next page. But first, I would like to thank Peter, Bruno, Yimin, Jeff, Zhenqiang, Chris, Alex, Ketan, and Greg for their comments during the progress of this document. In the current version of this document, we added the descriptions about the behaviors of mirror seeds and use IANA signed value 74 for this mirror seeds in the document. In addition, we made a few editorial changes. Next page. The behavior of mirror seeds is similar to the behavior of endpoint seeds for decapsulation and the specific IPv6 forwarding table lookup. The mirror seeds must be the last segment in a SR path and must be associated with IPv6 forwarding table. When a node determines that the destination address of a package is its local mirror seeds, this node will execute the behavior of a mirror seed. So this node basically will decapsulate the package through removing the outer IPv6 header and then forwarding the payload of the package using the forwarding table associated with this mirror seed. to distribute the payload over the package. So this is the first symbol and is already well defined for the end.dt6 seeds. So next page. Next page. So can you hear me? Can you move to next page?
But it seems like the screen sharing is lost.
Reshare.
Doesn't the next page just say solicit new work or something like that? I mean, can't you just talk over it?
The presenter is the screen by himself.
Can
Yeah,
you
the
hear me?
last page just comment and welcome, and we would like to ask for working group and last call.
That's all the slides you have.
Yes, yes, that's the last slide.
Greg, you have a question? Go ahead.
My question is related to the work that being discussed in spring on a compressed SRv6 SID. So because there's not yet a final decision, well, there is a decision to adopt CSID proposal. But it's just the beginning of the work. I think that it would be good if this document at least discusses how it's related to the SRv6 SID compression.
Yeah, I think this is a question for every extension for the seed, right? So for comparisons, I think this comparison, I think not every document about the seed to, so you possible can write something about a comparison, but I think that one is general for every extension regarding to this kind of a segment seeds, right?
Yes, I agree. It's probably more broad, but especially since authors of this document consider asking for the working group last call, I think it will be good to have the compressed SRv6 SID already considered and addressed in this document rather than have another document that would address their egress protection with the compressed SRv6 SID. But again, it's for the working group to decide. Thank you.
AC, go ahead.
AC Lindum, Cisco Systems. Given we have some documents for encoding of SRv6, we have one that is even further along than this, and I would be really against holding them until the whole compressed SID thing is sorted out. I mean, we can't wait for that. It's not like we're going to have compressed SID architecture approved in the before the next IETF. That's all I have to say.
Loa, you have something to say?
Just an answer to AC. I think what would be good was that when we start working group last call, we actually point at the compressed SID draft and say that there is a relationship, but we will go ahead anyway.
That's fine with me. I just don't think we should hold up any work unless it's on SID compression for the agreed upon SID compression architecture from Spring.
I agree.
Ron?
For Loa, I guess. If you point at the compressed SID draft, aren't you pointing at an unstable reference?
I took Loa's comment to mean you point at it in an email, not as a normative reference in any of the base SRv6 drafts as they go forward.
Yeah, I said that as part of the email that starts the working group last call, just tell people it's like a down ref. You need to notify people, but it shouldn't hold up the working group last call.
So for all the protection related draft, we will need to work with the Spring chairs on this topic anyway. So we'll sync up with them and update the working group template. Any other question? Okay, so the next presenter.
Okay, thank you very much. Thank you everyone for the comments.
Loa, I suppose you are in the queue by mistake. Lin, you are the next one. Lin, are you there? So it seems like we are missing a presenter.
Yeah, there's some problem with audio. It took me 5 minutes to rejoin.
Sheng Liu, the original number 4. Are you there? Yeah. Do you want to do the slide share yourself, or you want me to do it?
Could you please share the slides for me? Okay, that's it. Okay. And can I start now?
Yes, go ahead.
Oh, okay. This contribution is from China Mobile and Huawei Technology, and I'm Shen Liu from China Mobile, and I will give a presentation on accessing cloud via optical network problem statement. Next page, please. So the first page is talking about the motivation of this work. So as we know, as cloud-based applications are growing in popularity, data center and data center interconnection are becoming increasingly important. For example, financial service need low latency, high reliability. Government usually need large bandwidth, high security. Medicine services usually need large bandwidth, high reliability. And internet companies usually need large bandwidth and low latency services. So in order to meet this demand, data center international network are keeping migrating. Traditionally, people access the cloud usually by using IP networks. Alternatively, we believe accessing cloud with optical networks is increasingly attractive and becoming an option for user to access cloud, because optical transport network is basically based on TDM and time division multiplexing mechanism. So it doesn't have the queuing problem and can perfectly avoid packet congestion. Next page, please. Sorry, I can't see the page now.
It did move. So you should see use case 1 multi-cloud accessing.
Okay, okay, I see now. Thank you. And I will give several use cases for accessing cloud using optical networks. The first use case is multi-cloud accessing. We know that cloud services are usually supported by multiple interconnected data centers, which are usually within one region, spaced within usually 100 kilometers in order to provide active or virtual machine services within this kind of distance. So data center service usually require on-demand and scalability, high reliability, and user-based building, etc. This kind of requirement. So therefore, the network to interconnect the data center also require the high capacity and the low latency, high reliability, and flash scheduling, this kind of functionality. And we believe with advanced optical transport network, it's ideal for the DCI applications. For example, we can use OTN networks with VPN to connect multiple clouds together, and we have the ODU-K channel in between to connect this kind of clouds, and perhaps we have smart measurement and control systems for traffic perception, some kind of idea like this. Next page, please. Okay, the second use case is high quality leased LAN. High quality private LAN can provide large bandwidth, low latency, high security, and reliability. Actually, operator with optical network, operator with optical network can provide customer with this kind of high quality private LAN, which can enable user to move core asset to cloud side. By doing that, we can accelerate the deployment of cloud service and reduce the CapEx and OpEx. Next page, please. The third use case is cloud virtual reality. We know that the user experience of virtual reality largely depends on the local dedicated hardware, which can do rendering and something like that. And if we move the rendering function from local hardware to cloud side, we can improve the user experience and reduce the cost. But this raises a high requirement for the interconnection between user side and the cloud. We think optical network is an ideal approach to connect the user and the cloud for the cloud virtual reality. For example, it can provide large and sometimes flexible bandwidth. For example, from tens of mega bit per second to 1 gigabit per second, and the low latency. For example, smaller than 10 milliseconds and lower jitter. For example, smaller than 5 milliseconds. And next page, please. So this page summarizes the requirement for accessing to a cloud with optical networks. So optical networks with VPN can provide the capability of multiple to multiple cloud access. And actually, some OTN equipment has adopted packet processing functions such as packet switching, MPLS, VPN, etc. already. And also the second is high performance and high reliability. The third is small granularity container, and it can be tuned flexibly from 2 mega to 1 gigabit per second, and this can improve the efficiency of the network. Also, optical network can provide large bandwidth, low latency, and low jitter. So the last page, okay, I finished. Thank you. And the last page is our next step and our plan. We see two useful previous work within Tgwg related to this draft. The first one is net to cloud gap analysis. The second is net to cloud problem statement. We think the content in this draft is complementary to the above two draft. So we call for interest. So we call for interest and contribution. And I will stop here for questions and comments. Thank you.
Thank you for the presentation. And before we start questions, when do you say move forward together? Do you expect some kind of merge or just informal exchange of information? What are your intentions here?
To my understanding, so first, I think we should evaluate the common ground of my proposal and the previous work, and so as you stressed, maybe we can extend the previous work and merge something into it. That.
Okay, sounds great. Deborah. Deborah, you're on mute. Deborah, we cannot hear you. You are on mute.
Do you hear me now?
Yeah.
Okay,
Yes.
great. It seems I always have to do about 3 different mics. Okay. Just quick, because I noted this is also being presented tomorrow in CCAM. I just would like to say that I think this is really a CCAMP document, as it is addressing OTN requirements. And I would just like to say VPN work was addressed in CCAMP quite a while ago, 2005. So if any gaps are needed, they can address that. But they have done layer 1 VPNs already. And there's even another draft, RFC, I should say, 4974, which even adds more sophistication to that. And as far as the requirements on lower switching granularity for OTN, that's not an IETF discussion. That should be done in study group 15, who holds the rights to OTN technology. And it is quite an active discussion there. So if you need requirements on lower granularity, you should be going to study group 15. Okay, and then to tomorrow for further discussion. Thank you.
Okay. Should I? Thank you for your very good question, and for your first part of your question, I think we could just evaluate, for example, the GMPRs. Is that need to be adapted or changed to meet the new requirement for the accessing cloud with optical network, for example, multiple clouds. So maybe I think there's some work to do in this regard. And yes, I agree that OSU related work is mainly we should be mainly finished in ITUT SG15. Yeah, that's my idea. Maybe my colleague Hao Mian can give some his idea.
People in the queue, we are really tight on time. So unless your question is very short and to the business, please take it to the list.
I'm very happy to see the draft because, you know, we just posted similar drafts in IPv6 layer 1 year ago. So I'm very happy to see that, and we hope to have more discussion with you, the co-authors, and let's see how to move the world together in the future. Thank you.
Thank you.
Great, thank you. Here we are going to close the queue and move to the next presenter, please.
Excuse me. Chair, this is Hao Mian from Huawei. Actually, I would like to have a short question to the working group, because we see the 2 existing working group document has been expiring for a while. So we are curious about the reason, and to check with working group if we still have a chance to integrate what has been done in this document to the existing one. As the chair suggested, we can merge some of our common requirement and work on separate solution suggested by Deborah in different working groups.
So as Deborah suggested, this work probably belong in CCAMP, and we'll discuss it with CCAMP chairs, and we'll update you. We really have to move. We're over time for this draft.
Thank you.
Thank you. Next presenter.
So can you hear me? This is Lin. I just missed the last call from Yinzhen. I don't know. Should
yes,
I press
we can hear you. Yeah.
Okay, great. So should I share my screen or just use your?
Yeah, you can do the share screen like we practiced.
All right. Thank you.
Engine, we still see all slides. We need to unshare. Yep.
Do you see the? Oh, hold on.
Being started.
Yes, we can see our slides.
Yep.
Yes.
Great.
And
So,
probably you should go into presentation mode.
Okay.
So go ahead.
Hello, everyone. This is my presentation is about satellite network. It is a quite new area, and the satellite network is completely different as networking on ground. So it's quite complicated. And my presentation has two drafts so far. One is about problem and statement. Another is about proposal to use semantic address for satellite. Of course, it's not complete solution. It's just a tiny step to propose to use semantic address to improve the IP routing in the future. And I have presented this first draft in the Inter area before in last IETF. This time I want to bring it to a routing group, since I think the routing is one of the most challenging issues in satellite networking. So as a whole objective, this try to solve the routing and switching issue for large-scale satellite constellation network for internet access with a shorter latency and global coverage. And the right hand is a picture for the Starlink phase 1 satellite network. If you can see how big is the network. It has over 4,000 satellites. And right now it launched more than 1,500. So this kind of constellation is made from the low altitude satellites, 500 to 2,000 kilometers. And normally it has a couple of thousand or over even 10,000 satellites. And the inter-satellite link will be used to connect satellites. Even right now, even Starlink has not started yet. It's only does it in some experimental. And the satellite, it will be integrated with many ground stations by microwave or laser. And there are two types of ground station. One is called the gateway ground station. It can relay the traffic from satellite to another satellite. And also the gateway ground station is connected to internet. That's why we can access internet through the satellite network. And from this scale of network, we will have even more than 10,000 ground stations on Earth. And another type of ground station is called terminal ground station. It will direct connect to user terminal, just like our Wi-Fi router. And it may be able to do relay as well as suggested by Starlink. So this is an example of a Starlink plan for their satellite network. For the phase 1, it has 4 shares. A share of the satellite constellation is defined by the satellites with the same altitude and same inclination angle. So what is the problem of this satellite constellation? And satellite constellation is very dynamic, but well ordered. Every satellite position is keep changing at the speed of the first cosmic speed, or more than 7 kilometers per second. And but the satellite's orbit will be constant. With such dynamics, we can see the satellite network topology keep changing. Link state cost change very frequent. For example, link cost. If we use satellite distance as a link cost, then it will keep changing. And the satellite to ground station link, it also keep changing because the reachability issue. And it will have an interruption every 2 to 3 minutes for 450 kilometers altitude. And the links between satellites And for the latitude direction links, it's stated because their relative position is not changing. But for the links on the longitude direction, it will be unsteady at the polar area. I will show you later. And we will have 2 interruptions every cycle for the satellites. For this kind of altitude, every 1.6 hours, the satellite will move a circle on Earth. And also the links with satellites moving in opposite direction. Unfortunately, even with the same altitude, the satellites, adjacent satellite may move into opposite direction. And for this kind of link, they will interrupt every 3 to 4 minutes. All this calculation is in my first draft. And for vertical link with a different altitude, then it depends on the altitude difference and the inclination angle. So as a summary, satellite position is predictable by a mass, but not the links. Because link ground, for example, links between ground station to satellite, its quality will be impacted by weather and obstacles. And the links between satellites also impacted by tracking technology, because they will use a laser to track the peer, and definitely will not be 100% succeed. And also the distance is changing and position. So we can see that the traditional distributed IGP, BGP, MPS model is hard to use. Why? Because we will have a convergence issue for 2 frequently changed topology, and we will have a constant control data flooding issue because of the new topology, and also overhead of control protocol message for precious intersatellite link bandwidth, because from the current technology we can only have about 10 gig for the up to 2,000 kilometers distance. So how about the centralized SDIM model? Because last IETF meeting, some people said there's no problem for this. SDIM can solve it, but we can see it's impossible, because we will see where is the controller then, because we have so many satellites. Which one is the controller satellite? And what is the basic connectivities between controller to all satellites? We cannot have a constant connection between every satellite to one ground station. And how to guarantee the forwarding table on all satellites are synchronized, and how often the controller need to update the forwarding table. All this issue is not solved. The first draft, I have updated 2 sections. One section is analyze the adjacent orbit with the same altitude in non-polar area and the polar area. Then another section, I have a detailed analysis for the estimation of communication lifetime for satellites on adjacent orbit with the same altitude moving on different direction. So this shows the satellites on adjacent orbit. Even adjacent orbits may move in the opposite direction. And more complicated is that when adjacent orbit moving to the polar area, they have a crossing. So as a whole, there are 4 types of satellite links. One is that 1 and 2 non-latitude direction link, it will be relatively steady. But for the other links, all may be interrupted for a period of time. For example, link for longitude direction, it only steady at the non-polar area. At the polar area, it may be interrupted, depends on the tracking technology. I will show you why. And unsteady link is that between satellites, even on adjacent orbit, but with a different moving direction, then their distance will be changed faster. And so the lifetime of communication, it will be shorter. And the vertical links is between the satellites on adjacent orbit with a different altitude. That state depends on the difference of altitude and the inclination angle. So this is a situation when links come to the polar area. That's before crossing, that's after crossing. We can see the facing of the intersatellite link will be swapped. Right hand will become the left hand. I will have a video clip at the end, it will be easier to see. So new draft is that to propose to use a semantic IP address. If we embed the orbit and other information into the IP address, then what to embed? We have proposed 5 index: owner, share, and orbit plane index, and satellite index, and even interface index. Why we use interface index? Because the satellite interface is not like the router on ground that can have many interface, but in satellite, the price is very expensive, and we can only have a very limited number of index, so we can embed the interface index into the address. Then why we do this? First, the benefit is that we can make the link identification easier and faster. We don't need to have a satellite peer to exchange the orbit information before we know if a peer is kind of steady or unsteady. And also it can make the semantic routing and switch possible, but this one is not described in this draft. It's not mature yet. We will describe it after it mature. So how to use this semantic address? We have proposed 3 ways. One is IP address embedded into the interface identifier, and second is that embedded into the NIC field, but with a shorter length. Third one is used it as a variable length IP address. Why we propose this? Because as I said, the satellite link bandwidth is so precious. Directly use 28 bits in IPv6 interface may be too much overhead. If we have a shorter IP address, such as 48 bits or even 64 bits, will be a benefit for the bandwidth. So this is just coding, and this is IPv6 embedded into the interface identifier. This is a NIC field, and of course it will have a shorter fields for different index. And this is directly used as a IP address, but with shorter than 128 bits. Of course, it will be only we will decide the exact length after this variable length IP address is accepted by the community. Here I show the examples of links by this semantic address, how to distinguish different links and how to identify the status. For example, if we see the peer which has a satellite index difference is 1, that means it's on the same orbit and its link it should be steady. And if the link we see the orbit plane index difference is 1, and if it's my current position is at a non-polar area, the link issue should be steady. But if it's in the orbit plane index difference is more than 1, then I will know that my adjacent is moving very fast. The link may be not steady. Then for the vertical direction, then just check if the shear index difference is 1. If the shear index difference is 1 means that it's my adjacent orbit which has a different altitude. Next, I will show quickly the clip to visualize the dynamics of the satellite constellation. Can you hear? The sound is you can hear sound, right?
Yep, we can hear you. Not sound from video, so. No, doesn't come through. Very, very low. Lynn, it's too low.
Yes. You cannot hear?
No.
Oh, you cannot hear the sound from the video?
No.
Oh, sorry. So probably I just stop here. Everyone can check by themselves.
Yeah, Stephen shared the URL.
Email
chat
to the
so
list
people can
with the
watch it.
video link after the meeting, so people can
Yeah.
take a look.
Yeah.
Plus, we only have 5 minutes left for questions. Yes. Start, go ahead.
Stuart, you're on mute.
Sorry, it takes a couple of seconds to do all the microphone allowing. Lynn, at the very beginning of your presentation, you made an assertion that normal link state style convergence, normal routing convergence, would not be adequate for this. Mark Handley, who's well known in this community, did some simulations quite some years ago, and these were real simulations on a gaming engine, as I recall, for the whole cluster, and he concluded that it would work. So I wonder if you could resolve this difference of opinion between whether classical ordinary techniques work or whether we need to do something special.
Yeah, sure. Yeah, because just imagine if a network has a couple of thousand nodes, and many nodes will have a link interruption every couple of minutes, and for this kind of network, it will be very unstable in the ground network. So that's yeah.
You may say that he actually simulated the Starlink cluster, the whole thing.
Okay.
And concluded it was
yeah.
So we do need to resolve.
Yeah.
We do need to resolve this difference of opinion with fact.
Yeah, I know his paper, and I know his simulation. It's similar as I used, because this simulator software also from Serve. Yeah, I will check with
I
that.
just think that before we make assertions that it's not possible, we need to be clear what the real parameters are, and deal with that from a position of knowledge. And as I say, Mark was very convincing that he thought he could do it.
Mm-hmm.
Robin?
Huawei. But my question is that use the semantic address, what will be the forwarding table?
A forwarding table is because, for example, if you're using in IPv6, it will be same as for before. But the problem is that should we use a forwarding table? That's another question, because as I said, if we use a traditional technology, of course we will use a forwarding table. But if we want to use some new technology, we may not be able to use the forwarding table.
So because so that is just my doubt. So I mean maybe not the forwarding table. So I mean what will be the forwarding mechanism for this the new?
Yes. That's also I also want to have a community to be aware of this challenge. And if, as Steve was said, the traditional technology works very well, of course, we will still using forwarding table. But I'm very doubtful about that. If we don't have, we may need some new technology to make this work perfect.
Okay. The second one, I think this is will be the research work, or this is some of the working group work, because this.
Actually, I don't know right now. So I want the community make the decision finally, because I see some research work, but think about right now the many companies already try to deploy this network. So maybe we need some solution quickly to provide to industry.
Okay. Thanks. Okay.
Thank you.
Hi. So a very quick point first is I think this is a Manet problem, and I think it would probably experts in this area contribute to the Manet working group. This is a classic moving, adjusting network. The topology, although the number of nodes within your network is fairly constant because there's new satellites do not get launched that often, or they get launched at well-known periods. The topology itself is in flux, but it's in flux in a fairly predictable manner. So I think you can bound the problem, and I agree with you that perhaps the approach of some of the traditional link state protocols may not be right, but I don't think you have to throw the forwarding the forwarding table concept away. I mean, it's a fairly basic concept on which we pin a lot of IP on the concept of a forwarding table, and discarding that, I think, seems like a big step. I think you could add some sort of contact information within the forwarding table to say, at this moment your forwarding should be going this way, and after this moment it should be going that way, as the contacts change between the satellites. But still, that is deterministic and can be predicted. But anyway, either way, I think this would be a good topic to take to Manet.
Yeah, thank you, comments. But actually, your idea we did think about that way. But when we still encounter that some unpredictable events, for example, some adjacency lost, then distributed way may still not quick enough to synchronize all database. But we can discuss offline, because it's a very interesting topic. Yes, thank you.
And that's why I think Manet, because I think a hybrid approach between understanding that it should be there and some detection of whether that contact is there or whether it's slightly delayed or So, but this is the sort of subject that Manet deals with. Thanks.
Thank you.
Lynn, thanks for the presentation. I'd like to second, and Manet was focused on solving similar problem, lower scale. So, and I would really like you to focus on trying to address Stuart's comment. There've been proposals, there've been at least theoretical proof that things could work. If you could review it and provide this information, would be very valuable for the further discussion. And thank you.
Yeah, thank you. Thank you, everyone.
Okay, can you hear me?
Yeah.
Yeah, okay. Thank you. I am Wang Mingxue from China Mobile. So on behalf of other authors, I'm going to present this draft, the cloud and network integration considerations. So any suggestion and discussion are welcome. So next, please. So the motivation of this contribution is first to analyze the trends of network and cloud integrations. So with the development of 5G and the internet, plus the convergency trend of cloud and network is increasingly. So more and more services and applications will be carried on the cloud data centers. In order to support new services and applications requirements and meet the security and also the delay requirements, so the deployment location of the edge cloud data center is also lowered from the original DCs. So in order to avoid new construction of a huge cloud transport network, we consider the existing metro network to use to access edge DCs. So for example, in our company, China Mobile, so we use a 5G backhaul transport network, which is in IETF, the MTN technology, to access the edge DC. So the interconnection between the edge DCs and the regional DC or the core DCs is implemented through the coordination between the metro and the cloud transport network. So therefore, the access point of the enterprise entering the cloud is usually in the metro network, and the dedicated line entering the cloud also involves the interconnection between the cloud and transport, cloud transport and the metro network. In this draft, we describe the cloud and network integration scenarios and the networking technologies. Okay, now next, please. For the internetworking scenarios, there are mainly two scenarios. The multiple domains, so with or without the common border nodes. Okay, next, please. So the first scenario is the multiple domains with common border nodes. On the right side, it's a metro network, and the left side is a cloud transport network. So the boundary node of the cloud transport network also serves as a boundary node of the metro network. There are independent IGP instances in metro and the cloud transport networks. If the scale of the metro network is large, it will be divided into multiple IGPs. And for the consideration of the controllers, they may have different controllers or under the same supercontroller, like the orchestrator also. Okay, next, please. So the second scenario is the multiple domains with without the common border nodes. Also the right side is a cloud transport network, and the left side is a metro transport network. They do not have a common border nodes, and the border node of the two networks are connected by some direct links. So at this scenario, we need eBGP to deploy between the two domains to connect the routers and all the transport devices of the two domains. And we also need the hierarchy controllers in this scenario. Okay. So next, please. So we can consider the technology for networking depending on whether the macro domain support or does not support SRv6. The first networking technology with a metro network does not support SRv6. So we need segment splicing of the different network technologies to use to achieve the end-to-end connection of services. And for the second case is some nodes of the metro network support SRv6. And in the case of the multiple domain with the common border nodes, which is researched in the Spring SRv6 MPLS interworking draft, it can be used to achieve the interworking. Well, in the case of the multiple domain without common border nodes or other metro network scenarios, such as a metro network support MSTP or SR-MPLS, LDP, SRP, etc. The solution will need to be further discussed. So the third one is the metro networks to support SRv6. Also, in this case, solutions for interworking between two SRv6 domains need to be considered, and including the centralized controller and the distributed control plane solution, and how to implement the end-to-end traffic engineering, etc. Next, please. The above is our considerations on the cloud and network integration scenarios and technologies. So comments are welcome. For us, we are more focused on the case that the multiple domains with metro network and the cloud transport network with not without common border nodes, so they connected with some direct links. That is also real scenario in our operators networks, and further technologies will be considered more, and hope to see some comments on that. Okay, so thank you. That's all.
Thanks. Chandler?
I mean, it's really nice to hear the topic again, because we are working on this as well. So welcome to join the topic, and hopefully we can have more cooperation in the future. And as you know that we have posted a draft last year about the network, cloud network integration. We called it IPv6 based cloud oriented networking, and we list a list of the requirements and associated solutions in the draft, and I have posted the link in the chat box, and you can take a look, and we can have more discussion offline to take a look at how we can make cooperation further. Yeah.
Okay.
Shank, when you say we, do you mean the authors of the draft?
Sorry, Jeff?
When you say we, who do you mean? The authors of the draft?
Yeah.
That you published last year? Okay, clear. So please work together and see where there's any.
Yeah, sure. Because
could be done
both
together.
drafts, because both drafts are informational draft, and the scenarios and use case are really similar, maybe the same. Yep. So let's work together. Yep.
Okay.
Great, thanks. Next presenter, please. Stuart.
On me.
Thank you.
Right.
Still in the queue. I assume you don't have any questions, right?
I don't have any questions, no.
Okay.
So, preferred path routing. Next slide, please. Right. In this talk, I want to do two things. I want to give a 2-slide reminder / revision of what PPR is. And then I want to look at the use cases that we think PPR would be advantageous to deploy in. And then I'd like to encourage others to work with us on this technology. So next slide, please. So here's a quick overview. PPR provides a method of injecting engineered paths into link state IGPs. In the data plane, the packet is mapped to its intended path by the PPR ID. The PPR ID is a single identifier in the packet. So just one address of whatever type the packet is using. But it can support multiple data plane types. So the PPR ID can be an IPv6 address, an IPv4 address, an MPLS label, an MPLS or an IPv6 SID, or a MAC address. So we can apply it to any of these technologies. It's not hemmed into just MPLS or just IPv6. So here's an example on the left of a packet that's going ABCD. In the data plane, the only thing that maps it to ABCD is the PPR ID, and the path is described in the IGP. All right, next slide, please. And there's a draft that describes this for people who want to remember how it works. Next slide, please. Right, thank you. So it can support quite a rich range of structures. We can describe point to point, we can describe multi-point to point, and we can describe graphs within the control plane structures that were designed for this technology. The PPR path can be injected by a node for its own purposes. So locally, I can decide I want to construct a PPR path. I just inject it into the IGP like I would any other LSP. Or it can be injected by through an SDN controller, you can just create these paths, right? So, but what it really does, what the really important characteristic of it is that it enables engineered paths in cost-sensitive network applications. So think cheap hardware, the cheapest hardware you can imagine. Think small overhead, because packet overhead is a problem, and think a relatively simple operational model. And we have an open source implementation of this that was demonstrated some while ago at IETF 105. So next slide, please. Next slide, please. So here's some use cases. All right. So here is a mobile backhaul, a mobile crosshaul. And the thing we're interested in is in those little purple circles. And they are where we need to provide cheap connectivity. And at the moment, they're provided by a number of technologies, layer 2, IPv4, MPLS, IPv6 underlays. It is by no means a world that's gone entirely to IPv6 and not necessarily even to MPLS. Next slide, please. So let's drill down a bit. Here we have what one of those circles, little pink or mauve circles look like. All right, it's actually got structure, and it's got structure in which we have to do traffic engineering. It's usually a set of large subtended rings of various sizes. On this structure, we need to provide slicing, because this is the world that slicing was created to serve. But we also need to apply things like, and that slicing will need strict paths, and it will need traffic engineering. We also need to provide fast traffic engineering aware fast reroute in this environment. So, you know, think, how do we do this for the minimum amount of money on the cheapest hardware, much of which is actually already deployed and will cost a lot of money to change? Next slide, please.
Stuart, while you're continuing,
Sure.
I think ST asked for clarification.
So go ahead. Go ahead.
How would you contrast this to a binding SID?
We're going to talk about that. Wait. You can use it to create binding SIDs. Let's get there in a moment.
And I'm not a plant.
Right. So, but we will get to binding SIDs. Right. So, leaf spine networks. Think about the edge of the network, right? In the edge of the network, we're going to have to put some mini micro data centers, right? Because the trend is to get these computes out as close to the user as possible to save bandwidth and to improve latency. So these tend to be leaf spine edge fabrics. These are not massively scalable data centers. These are small systems. They use an IGP, and they've got an IPv4 data plane in many cases. They will need to produce to support traffic prioritization, and they will need to support redundancy and granular path level OAM. Next slide, please. Fast reroute. All right, so we discussed this a little while ago. The interesting diagram on here is the purple line, which is a traffic engineered path. And what we need to do is to traffic engineer the backup for that path. And we don't want to wait for end-to-end recovery, because that takes too long. We lose too much traffic. We don't really want a controller to go and control everything. We would like to do this with some sort of more classical fast reroute approach. So local detection and a path that is suitable for repairing from this point, which may be different from a path that's suitable in another point. So we may have to put a number of these in, and we may need to merge them. And we showed in our draft RTGWG PLA how we could do that. Next slide, please. Right. So this is AC's question, right? So there are other uses for this. One of them is as a complement to segment routing. It can be used as a method of creating binding SIDs where you want to inject a number of properties associated with those binding SIDs, such as what the precise fast reroute strategy, what queues to be used, what bandwidth to allocate, etc. We can also use this as a method of providing TILFA in IPv4 and Ethernet networks, and also in MPLS and SRv6 networks where the overhead is critical. Because the nice thing about this is one identifier gets you there. So we see this as a way of adding binding SIDs to a network. But it has a number of other properties, right? So for example, just skipping one for the moment, there's no algorithm metric needed. The path is the path you needed. You don't need to trick the path to go where you want it to go. And so you can put an exact path in, and also you have no constraint of 128 paths, which is the algo limitation on Flex Algo. We believe the method is suitable for underlays such as VPN Plus. And another area that we're starting to explore is energy efficient networks for industrial verticals, where the path you use needs to be changed in order to maintain the sort of carbon set up and maintain the carbon footprint that you're trying to achieve. Next slide, please. So that is a 9-minute introduction as to what PPR is. It's an introduction to what we think the problem space is that this maps nicely to. So has anyone got any questions, and is there anyone interested in collaborating with us to see where we can take this approach?
We will start with Peter with questions. Guys, please be quick. We are really tight on time.
Peter.
Well, Tarek, you were first. Okay, thanks. Hi, Stuart. So I have a question regarding the scale. I mean, you are trying to save the overhead in the packet for the price of putting the overhead into the IGPs, because you propose to advertise the mapping between your identifier and the path. I mean, if you have many paths, how scalable it is to put this in the IGPs?
Well, we think it's scalable, particularly as a lot of these networks are relatively small, so we think, for example, in a mobile phone edge network, we think it'll probably work. We're not talking about doing the whole internet. We're not talking about doing the whole core this way. We're talking about edge, cost sensitive in all of its terms networks that may want to map onto existing hardware.
Well, I mean, your argument is we can do more algos than 128, etc. So I assume you would have more than that number of paths and varies between various endpoints. So that adds to the scale.
Right. So I think there's some work done which hasn't been widely discussed on how to reduce flooding reduction for this as well. Because you don't need to flood this outside the zone where you're going to use it, and you know where it's going to be used from the information in the packet.
Well, okay, well, that's my concern. I mean, there's a lot of stuff put into the IGBs. All right, thanks.
So
yeah, it's always a trade-off. Go on.
Thanks, Stuart, for the presentation, and thanks, Peter, for giving me the chance to speak. So my question is that there is a per path state here stored or maintained on every node in your IGP domain, right?
Well, so we think we can do flooding reduction on this. So it would be it'd definitely be stored on every node that needed to know about it, but that's not an unreasonable requirement.
So, Stuart, we had thought about similar approach, but it's rather than relying on IGP, we used RZP to set up this path along the nodes.
Tarek, who are we? When you say we, please
there is a draft
that
myself and Pavan pushed in traffic engineering working group, T's working group. So it's similar approach, but rather than relying on IGP, we relied on RZP. I don't know.
So this fits in with the current philosophy, which is to get rid of RSVP and rely and get rid of for example, the MPLS protocols. That's one thing, right? And secondly, RSVP really only works with MPLS, and this will work with anything, including one of the things that we looked at was couldn't we apply this to link state Ethernet systems? So this will also apply to V4, which is really the sort of poor child in all this. But the reality is that there is V4 out there.
Exactly, that's what I was trying to say. The draft we wrote was addressed for IPv4 and IPv6 TE, but I understand your response. There is per path state maintained in IGP. That was the answer. Thank you.
Andrew, please be quick. 1 minute.
Yeah, just
we cannot
very
take
quickly. Stuart, I just wanted to say thanks very much for the draft. I hadn't gone through it before this meeting, but in answer to your question, if there's anybody interested in working with you on this, 100%, because I really like the philosophy of this, and particularly within the African ecosystem where we do have a need for lower cost technologies, etc., with a lot of our clients, etc., this is really a very big interest to me. So thanks very much. And if you do need someone who's going to work with you on it, 100%.
Thank you, Andrew. Really interested to know to work with you, particularly on understanding the use cases. But you're welcome to work on anything else. Is it G next or?
No. We are going to cut here. We are over time.
All right.
G,
Okay.
please take it.
A quick comment. I see you
All right.
mentioned network slicing
G,
and
please take it to the list. We are over time already.
Oh, okay.
Next presenter, please.
Hi, can you hear me? This is Gian.
Yes.
Can you hear me? Okay. Hi, my name is Gian Mishra. I'm with Verizon, and I will be presenting the updates on the APN framework and gap analysis on behalf of.
So as we said before, we are really interested in changes, and why do you think this should continue? Because you've got both. This is probably third or fourth presentation. Please focus on the changes, not on the material itself. Because we've seen it before a couple of times. Okay.
Thank you, Jeff. All right. So the changes and updates to this the framework, and just kind of carrying on from the lab. This has been presented a few times. So, and I think what the goal of this presentation is to help provide more clarity to the APN solution and what the gaps that exist today, and the solution that this provides, and how this fills the gap. So what I'd like to do is walk through this scenario and really help depict kind of this use case and how it applies, and then just go over the gaps and where the gaps exist today in current and existing solutions, and where we're really have a fit for APN. So to start, I'll walk through this. This is basically an office productivity scenario, and what this does is, I think to Jeff's point, it really kind of goes to the updates that we had to APN. It really is clarification of what APN provides, and that's with this use case. What I'm trying to do is really clarify and help everyone understand kind of what this does and how it helps move the ball forward. So with that, this use case, so it's described in section 6 in the APN framework draft. Basically, it's a typical office productivity scenario where you have a branch office. It sits in domain 1 in city A, connects across an operator backbone, connecting to cloud applications in city B, connected to another, within another metro network. So very typical office productivity scenario. In this use case, we're in this case, it's an IPv6 underlay, so we're using SRv6 end-to-end traffic steering with an L3 VPN overlay. So just a typical scenario. Next slide. So this is really this is really the main update, and then what we're doing is trying to provide more clarity in how this can be used. So APN, because it's providing an ability to allow for the same deep packet inspection that you get with QoS, now we're actually doing it with an APN ID that is that ID that is encapsulated, added to the packet. So with that APN ID, because it's in the outer header versus deep packet inspection, you're able to get that fine-grained information at the outer layer. So it saves on hardware, memory, CPU resources, and actually going through the deep packet with that APN ID. And with that, being able to provide, and this is really one of the use cases, but being able to provide endpoint connectivity access control capability, similar to an ACL, but now we're doing it at the network layer, being able to provide it with traffic steering, where we're able to take a user group. So let's say in this office productivity scenario, we have a user group who's accessing cloud services. And so with those cloud services, you have within the APN ID encoded, you have a 5N tuple of headers that define the application flow. And it could be any typical, in this scenario, we're showing voice, video, and data traffic. So that traffic gets matched with a source IP, and then it gets set to a user group. So that specific user group is part of that endpoint application flow that's defined in the application ID. And then with that, it's matched to that source and destination, and then it's set to the user group is now set to an application group. So we have the source get set to a user group, and then that is actually classified to an application group, so discretely to control the that fine grain. And this is really where the action happens with APN, being able to provide that fine grain on an application basis. Next slide. So with that, with the access control, what this depicts is in that endpoint control of end user application control from a particular user group, mapping that to an application group. So here what we're showing is we have a user group defined 1001, and then here we show that there are other application groups that exist, and so we are explicitly denying so that application user group does not have access to these particular destination application groups, and it only matches the 1001, the ones that we wanted to have access to. So the 1001, 1002, 1003. So those are permitted. So providing that fine grained application control from basically source destination, layer 3, layer 4 flow. Next slide. So with that same concept of taking with the fine grained information, the five tuple sort layer 3, layer 4 information, defining it, mapping to a user group, and then matching that user group, mapping that to an application group. Now with that, instead of having to do any type of deep packet inspection to determine where I want to apply, let's say if I need IOAM, like OAM services to get telemetry information for a particular application flow. It could be like voice or video or something that has high jitter latency. Could be across like a 3GPP user plane or whatnot. But let's say you want to apply IOM just to that particular flow instead of having to require deeper packet inspection to go into the payload. Now you have this outer header, this application ID that's added to the payload, but I'm not added to the payload, but added to the outer header, so you don't have to go deep into the packet. And that information is right there that you can match. So saving on hardware, resources and latency and processing of the packet, and to apply and any IOM characteristics for telemetry. And then once that's done, now at the head end of the APN infrastructure, now we're able to match. We got the classification done with the matching. Now we can redirect that flow and we can steer to that particular SRT path can now be instantiated. Next slide. So as far as gaps, I know in the last presentation at IETF 111, we did go through a lot of the gaps that exist. So I just wanted to touch on those again. And this is something that there was a lot of question. We spent a lot of time on this, but really the bottom line is that there are existing solutions, and what APN does, it provides its own. It provides a solution to for this fine-grained SLA capability. However, in looking at the existing solutions and mechanisms, and just looking at what we have here, DetNet with the flow ID, as well as network slicing with the resource ID, or as well as service function chaining with the SPI identifier, they all have their own particular function that they're used for. but being able to leverage those existing functions to actually provide that same type of fine-grained SLA isn't possible because they have, and you can't really use, these already have their predefined function, so you can't really use this for another function, this, such as the fine-grained SLA, and that's where the APN ID, having this new structured section or intelligent ID that's able to provide this fine-grained service. I mean, that's really kind of the big thing. And we did talk about other existing mechanisms like the flow, like the IPv6 flow level, and that was discussed quite in depth. And the issue that exists with the IPv6 flow label is that even with RC 6437, they do mention in there that that stateless ECMP load balancing, is supported in conjunction with stateful signaling. However, the details of that is out of scope of that document, and there isn't any, even from 6man in discussions, there isn't any use case or scenario where that's even possible. And even in discussions with 6man, just in related to that, it's either one or the other. And if you're using signaling, and there are some other drafts that talk more in detail, or RFCs that talk more in detail, but if you're either using the flow label for signaling, but then that would actually break ECMP, and you really can't do both. So that's the big deal there. The other thing that was mentioned, I guess, was QoS. And QoS, so what QoS provides, I mean, that's been around for decades, and it's provided really a means, providing SLA, but what I would call core string, but it does provide SLA for classifying traffic. What this does kind of goes above and beyond that, because now it's able to do some more ACL type, like infrastructure ACL type endpoint flow management, as well as being able to provide that same QoS type of traffic classification and prioritization, but now taking it kind of to the next level, a finer grain of classification. Next slide. So in the gap analysis, this slide just kind of shows kind of all the different existing solutions that exist, existing mechanisms that have used for existing technologies today. So what we feel is APN would be positioned for not only existing technologies, but as well as future technology. Then it would also enhance any existing solution or technology that exists. Let's say, for example, QoS. This could be used in conjunction to provide a finer grain of application flows, similar to kind of what I'd shown in the use case with being able to classify a further classification of interesting traffic with an ACL, but more granular. So taking what you have with QoS, but now applying ACLs to that and being able to do a more robust classification of characteristics and being able to map them to discrete traffic engineer flows. So in here, we go through IOM, DetNet, and all the other flows that I mentioned, the other mechanisms that exist today. They all have their discrete function that they're used for, but then taking those functions, those mechanisms that exist today, and being able to leverage that to actually use it for APN, and what we're showing is that is not possible. They serve their function. They're good. That's what they're made for. But being able to leverage it to be used for APN would not be possible. And that's really why APN really kind of the selling point on APN is what it can provide, and really the gap that exists, that existing solutions really are not there that they can provide that solution. Next slide. Thank you. So any comments, questions for anyone? I hope as I went through that, if anyone has questions or comments, just to help, I can try to help explain. And I guess there's a couple other slides, decks that we're going to be going through with Robin shipping as well. Thank you.
We'll have one comment. Tarek, please go ahead.
Is about the ID. Are you looking for per flow ID or per group of flows ID? I didn't catch that from your table.
Sure. So again, because it's granular, it would be, the flow would be, it could be an aggregation of flows. So anything coming from a CE, it would be an aggregation of flows. Or
Okay,
it could be a
because
single
flow
flow. I think it's granular enough that I think if you had to because it's based on ACLs and source destination, you really could have it as fine as granular as you would like, and that's up to the operator. You know how granular you would like to make it.
the reason I'm asking is, I presume flow ID is already known, right? You can have a flow ID embedded in a flow label, for example.
Yeah.
Okay.
Understood. Thank you.
Thanks, John. Next presenter, please.
Rick, you can ask the question. Meanwhile, I will switch the slides.
Oh, okay. Thank you.
Make it quick.
So I'm glad you mentioned QoS as the kind of the de facto standard for labeling application flows in existing edge networks. One of the nice properties of the QoS bits, of course, is that when you're traveling across an IPsec tunnel, QoS can be promoted. Do you consider the APN information, the header information, also being sort of carried from the inside of tunnels during the encapsulation process to the encapsulating packet? Is that in your model? Have you considered that at all?
Yes. So let's just so I understand. Yeah. So the APN ID, it would be encapsulated and it would be part of the so the data packet that gets transmitted. So that the APN ID would be in the in the packet and throughout the APN domain, so throughout that flows domain, and then removed at the egress point of the domain.
Okay. I really like this, by the way. I think we've been desperately searching for a solution to this, but we haven't realized it as the IETF. So I totally support this. Thank you.
Thank you. Thank you.
Robin, please go ahead.
Okay. Okay, this is Zhenbin. So from Huawei, I will introduce the encapsulation of the APN. So the encapsulation including the APN header, and also this is the the data plane IPv6. So means the IPv6 encapsulation for the APN header. Okay, next page. Okay, so according to the APN framework, so that's the APN header can be easily be abstract. So here we can see that's we have this the APN ID, because we have the different maybe we have the different scope for the APN ID. So here defined the two types of the APN ID. One is the short APN ID is 32 bits. Another is a long APN ID is 128 bits. And also that's the APN ID is mandatory in the APN header. Besides the APN ID, there's the two optional the fields. One is the intent. So this means the represent the set of the service requirement to the network for specific APN ID. And also that's we also have this the APN parameter. So that's this the APN parameters defined for the specific APN ID. And also in order to indicate if the specific APN parameter exists or not in the APN header. So we have the fields of the APN parameter type. So it's a 16-bit identifier. Is use each bit to specify which APN parameter exist exist in the APN header or not. So that means it's a bit map. Okay, so this is APN header. Next slide. Okay, so API ID can be divided into 3 parts. So that's first is the API group ID and the user group ID, and then this reserved. So the length of the APP group ID, user group ID, and the reserved fields can be variable. So this can be configured in the domain and be consisted in the specific network domain. Okay, next slide. Okay, so here we defined that's the 4 API parameters for the network service requirement. So that's this is the bandwidth and the delay and delay variation and the packet loss ratio for the specific API ID. Accordingly, we will define this the 4 bit for the API parameter type. So that's each bit to indicate specific API parameter exist or not. Next slide. Okay, so this is the IPv6 encapsulation for the API header. So we defined that's the option. So that's the one. This is has defined this is the option type and the data length. Then this is the value. The data option data. The option data is just the API header defined. So this option can be used in the hop by hop option header and the destination option header. Besides this, the API option used for the extension header, because we know that for the SRH there's the option Tgwg. So that's the APN can be also used combining with the segment list. So we also defined this the APN Tgwg used in the SRH. So here this is the format. It has the type length D flag. So then this the data is the APN header. Okay, that's all. Okay.
Let's go to the next presentation, then ask question if any after that. Chopin?
Okay, so hi everybody. I'm going to introduce you about our new work on the control plane and the management plane. Next, please. First, about the flow spec. And we define a new flow spec component, APN ID. And here is the encoding. We use the mask to indicate the base of the APN ID carried in the packets and to be matched against the APN ID carried in the flow spec. So here, this diagram shows an example. And you could see that the mask is used to match the APP group ID. Next, please. And we also defined a few traffic filtering actions, and they are used to mark the APN ID in different ways. And we could mark the entire APN ID or a partial APN ID. And for the inherit is that when the APN ID is already carried in the package, when it go into an outer tunnel, and this APN ID could be inherited, and that is copied and encapsulated in the outer tunnel header. And also for the stage action, that is part of the APN ID already carried in the packets, will be staged with the part of the APN ID carried in the flow spec. So those two parts will be integrated into one APN ID. Next, please. And here, and the ordering of the flow spec is also important for APN. There are two reasons. One is that there are also other coexisting flow spec rules, and besides the APN flow spec rules. And also because we know APN ID is structured, and different parts of it can be decided by different rules. So that means we need to have a careful organization of those rules. Here we introduce this new EC, and we have the group ID and the subgroup ID. And for within the subgroup ID is actually the same as what we have previously defined. That depends on whether the traffic action is carried or not, and whether the T flag is set. And when one condition in the subgroup is matched, the evaluation of any subsequent flow specifications within this subgroup will stop. And between subgroups, that is because each subgroup contains the rules for tagging the one part of the API ID. So all the subgroups will be evaluated one by one. And between the groups, we give the group with priority, and that means once there is one condition is matched in a group or in the API group, and the following evaluation will stop. Next, please. So here is about Young model. And there are a few parts of this Young model. Currently, we only focus on the IPv6 data plane, and we define global action that is for the inherited, which I just introduced. And then it's about the API ID templates, and to define the templates for this structured API ID. And for the marking, and we could mark the API ID based on the templates we have selected. That is once you select the flow and then you tag the API ID. And last is the mapping policies. And we could use color to differentiate mapping policies to indicate those different set of mapping policies. And then based on the API ID, we could decide which as our policies to go into based on the color. And it could also be the redirect to the next hop. And that belongs to the native IP. Next, please. Yes, that's all. Thank you. Any questions?
Greg, please, one and very short question.
I think that would be good to get more information on the list on what their expectation of having in the profile packet loss ratio and a jitter. So I understand that that's to be added in IPv6 encapsulation for APN. So what their expectation of how that can be used? Is it constrained for forwarders or local path selection or such? So just let's discuss it on the list.
Thanks.
Thank you.
And next presenter.
Hey, hello. Can you hear me?
Yes.
Hi, this is Ray from Alibaba. We're going to present how we're going to precisely control the congestion inside network. And that also relates to how we choose the route inside the data center. Together, we contribute to the low latency networking for our applications. Next slide, please. So today's new applications such as high performance storage and the large scale deep learning applications use new hardware that can generate data orders of magnitude faster than before. So that requires a low latency for the network, and also that network become more important than before. And another trend is that resource disaggregation is happening inside the cloud, which is separate the compute and storage and the memory into different separated resource pools. So even memory access will go through a network in the future. So that means that we will add considerable load to the network and also require ultra low latency. So how we're gonna solve this issue is a question mark for our future. Next slide, please. Next slide, please. Hello?
Injin, can you progress?
Because due to the slow down of the Moore's law and the CPU cannot keep up with the traffic rate, so there are lots of effort to offload the computing and the data transferring workload to the hardware, such as the RDMA and the DPU. However, using faster hardware that can generate data more aggressively that causes severe congestion inside network. Next slide, please. So we observed a couple of issues in today's congestion control inside high-speed network. First of all, is that those network has to use a flow level flow control, such as PFC, to reduce the packet loss. However, due to the PFC storm and the deadlock happening inside the clouds, which caused a stability issue of our network. And this whole reason is because that the congestion is have a slow convergence time. So that's why we cannot resolve congestion in time. The second issue is that we cannot run multiple applications together inside the cluster. And we're using quality of service queue cannot solve this issue because QSQ is very scarce resources, which has been allocated to different applications. The reason behind this is that existing solution using standing queue to identify congestion, and the standing queue itself being an issue of latency. The last one is today's congestion control solution using many parameters to using heuristic approach to adjust the congestion status. Next slide, please. So there's a new trend inside the switching silicon is that in-band telemetry. So new switching silicons has in-band telemetry ability. If, for example, inside this figure, that when the packet goes through the switch can add a telemetry information into the packets. So each switch can add some information into the packet, and those packet and the telemetry information can be redirected to the remote collector to find many use for troubleshooting purpose, such as where the packet get lost, is any routing black hole, etc. The next slide, please. So with this new opportunity and primitives of in-band telemetry, the question for us is that can we use that information as a precise information for us to do congestion control? So that's the original idea, which we call the HPCC. And so when the packet goes through a network, and each switch along the path will add telemetry information into the packet. When the packet arrives at the destination, and the receiver can generate notification packet or ACK packet back to the sender to adjust the sending rate. Next slide, please. So in HPCC, we define the algorithm to using those telemetry information for congestion control. Those information including the queue length, transmitted bytes, timestamp, link capacity, etc. So we actually define how we can use those information and how we can calculate the precise sending rate based on that. However, the actual packet format is dependent on the environment. So here we give an example of telemetry being embedded into the a certain telemetry format. And the green color show that information we utilized and we defined in HPCC. Next slide, please. So when we use this approach to precisely identify and control the sending rate, we solved all three issues previously mentioned. First of all, we achieve faster convergence because we know precisely how much we can send to the network without causing the congestion. And secondly, we know that we base our information based on the telemetry information, not based on the queue length. So we actually don't require a queuing in the switch, so we can actually achieve a near zero queue to achieve both high throughput and low latency. And because we know precisely what's going on in the network, so we don't need heuristic approach to guess what's happening inside network. And that's why we use very few parameters. Next, please. So so that also relates to the routing inside network as well, because route condition changes dramatically inside data center. For example, incast can happen quite frequently, and link failure due to routing black hole, and also silent drops can also happen in particular routes. And application want to fast reroute to a different path to avoid this temporary failure or partial failure. So rerouting is a kind of a network primitive provided for application before the application get affected. So HPCC actually using this precise information to kind of have a view of a route capacity. We know how much traffic we can send to a particular route. If this route has failure, which means that there's a zero capacity, we must do the reroute as soon as possible. So joint with the routing and the traffic allocation, so we can have a combined view at the endpoint side to decide how much traffic we can send to each route. If the bad condition happen, we can switch the traffic to a different route to avoid the impact to the application. Next, please. So let's give our evaluation results in the production. When we implement into the SmartNIC, we see that the traffic actually been, the latency has been reduced to up to 95% in the small messages. If you look at the left figure, and that's happened because we actually control the queue length and resolve the congestion. If you look at the right curve, which shows the distribution of the buffer usage inside the switch, and even in the 99th percentile, we only have a 23 kilobytes buffer inside the switch, which at only a 7 microsecond delay. Because for many applications, every microsecond matters. So we need to reduce the latency as much as possible. Thank you. That's the end for my presentation. And if you are interested in working with us to collaborate on this topic, please email to us. Thank you.
Thanks. And we've got Robin in the queue.
Quick. So I want to know the purpose of the draft. Is it define the framework or is it tried to propose some of the protocol extension? According to my understanding, because we know that already has the IPPM working group, that's the in-band telemetry. And also we also have this traffic engineering work in the RTG area. So what's the work of the HPCC plus?
So IPPM is defining the format of the information being put into the data packets. So our work is define the algorithm because this algorithm has to be implemented in both the end host in the switch along the path. So it's from different vendors. So we want to have a general agreement on the algorithm and the protocol, so we can coordinate with different part of the net inside network to work together. So that's the purpose. Is we want to provide a kind of a framework and a protocol, so to define especially how the algorithm works. And beyond that, because that's also related to the how we choose the different routes based on the condition of each route. So that also require the software part to be aligned with hardware implementation.
Okay.
We are over time. I think it's really interesting work, and I mean, we are very, very far away on distribution of reachability. However, this work brings also knowledge about condition of the network and also notifies both sender as well as transport nodes. So we'll be working with authors to provide kind of better alignment with what routing area is all about. But I think this is something we really need to work on. This step is coming up. Artificial intelligence is being deployed in all large data centers, and today's IGPs and BGP doesn't address it. That's why you see the presentation here. We are over time. I would like to thank everybody in MicroShare Engine. It's been a really great meeting, and I really, really hope to see you face to face next IETF. Have a great day, and see you next time.
Yeah. And we are sorry we couldn't let the BFD presentation happen because we are really running out of time. So. See you next time.
Bye, everyone.
See you next time.